Heats of formation. You need your book on page 510. The standard enthalpy, or heat of formation, delta HF, F here is standing for formation. So it's the change in enthalpy, or the change in heat, which occurs when 1 mole of the compound is made from its elements. So because we're talking about having 1 mole, when we balance these reactions, we can have fractions. Because we want 1 mole, when we balance, fractions as coefficients are okay. So in our first example here, we want gaseous carbon dioxide. So our product then is going to be CO2 as a gas. Now what elements make up CO2? You have carbon and oxygen. Oxygen is a diatomic. Carbon is a solid at room temperature, and oxygen is a gas at room temperature. This reaction happens to be balanced as is. So then we can look on page 510, and we can see that carbon dioxide has a delta H of formation, or heat of formation, of negative 394 kilojoules per mole. So if I wanted to have 2 moles of carbon dioxide, I would just multiply this by 2, and that's how much heat would be released when we made 2 moles of CO2. If I want half of a mole of CO2, then all I would have to do is divide this by 2 to figure out how much heat is released. In our second example, we have aluminum oxide. So we cross our charges, and this is going to be a solid. It's made out of our elements aluminum and oxygen being a diatomic. I need 2 aluminums in this one, and I need 3 oxygens. So what times 2 is 3? Well, that would be 3 halves, or 1.5. Again, it's okay to have that fraction. So aluminum is a solid at room temperature, and oxygen is a gas. And then we can look at our table, and we can see that the heat of formation of aluminum oxide is negative 1680 kilojoules per mole. Now we're not usually just adding elements together to get compounds. Usually, most of the time, we're multiplying or taking compounds and mixing them together. So there's got to be a way of looking at heats of reaction when we have more than one compound. This is where Hess's law is applied. Hess's law, we can do the math 2 ways. The first way is by saying the products minus the reactants. So these values are in the back of your book on page 921. It's one of the appendix. Remember that on the right side of the arrow, we have our products. And on the left side are our reactants. So my heat of reaction is going to equal my products. The first product I have is aluminum oxide. There is 2 moles of aluminum oxide from the coefficient. So we're going to say 2 times, and then I'm going to look at my chart for aluminum oxide, and I get 1675.7 kilojoules per mole. I have another product, so we're going to add here 3 manganese. So 3 times the value of manganese is 0, minus our reactants. So I have 4 aluminum, so we'll say 4 times. Now you might notice that aluminum is not on this list, and that's because elements in their standard state are always 0. So again, elements in their standard states are always 0. So I know that I'm going to say 4 times 0. Then I have a second reactant, so we'll say 3 times the value of MnO2, negative 520.03 kilojoules per mole. And then all I have to do is plug that into my calculator. And so my heat of reaction is negative 1791.31 Sig figs, it's the fewest decimal places. Here I have 1 and 2, so I'm going to go with the fewest and say 1 decimal place. Kilojoules per mole as my final answer. Now, because elements are always 0, we actually don't even need to include them when we do the math. So if you recognize that elements are 0, you don't even have to have that part in the math equation. Alright, so here's some more examples. Remember, it's products minus reactants. So my heat of reaction is going to be my product, calcium oxide, plus my value of carbon dioxide, minus my reactant, calcium carbonate. I guess I don't really need a parentheses there. And then all we have to do is plug that in. Something to keep in mind is that when you're doing the math, make sure you watch out for those negative values and coefficients. This example doesn't have any coefficients, but you would want to take those into account if they had some. So my answer then would be 178.3 kilojoules per mole. For my third example, heat of reaction equals products, and I have 2 of these, so we're going to say 2 times the value for NO2, 33.18, minus my reactants. Both of my reactants are elements in their standard state, which would be 0, so I'm not even going to write them down because they do nothing for us. So my heat of reaction then is 66.36 kilojoules per mole. And then our last example, my product here is 2 waters. Now when you look at water, there's actually 2 different values, one for gas and one for liquid. So that is important to keep track of which one you're using. Oops. Oxygen is an element in its standard state, so I'm not going to worry about it. Minus my reactants, 2 times hydrogen peroxide, and then simply type it into the calculator. And we would have an answer of negative 196.1 kilojoule per mole. Notice that these first 2 have positive delta H values. When delta H is positive, it's an endothermic reaction, so the first 2 are endothermic. My last one here, delta H, is negative, so that would tell me that this is actually an exothermic reaction. The second way to figure out the heat of reaction is to manipulate the reaction mechanism. So our reactions don't always occur in one step. Usually it's a series of steps that are taking place. I can change those steps so that when I add them together, I get my overall reaction. So whatever I do to my step, I'm going to do to my delta H value for that answer. So if I look at the first example, I need 2 COs as a reactant, which I have right here. So I don't want to change this reaction at all. I don't want to change this delta H value at all. I'm sorry, there's a typo in this problem. Let me fix the typo. Alright. I need 2 NOs as a reactant. Well, my NO is sitting down here, but it's listed as a product. So I need to flip this reaction. So I'm going to make my reactants products and my product the reactant. So I've flipped that reaction, which means my delta H value needs to also flip its sign. So this is going to be a negative 180.6 kilojoules. So then there's my reactant 2NO. I need 2 CO2s as a product. Here it is as a product. And 1 N2 as a product. Here it is as a product. So when I go and add my reactions together, so I'm adding these reactions together, I would have 2CO plus O2 and 2NO as reactants. As products, I have 2CO2, N2, and O2. So if you notice, we have oxygen on both sides of our arrow, which means they cancel out, just like our spectators did. So if you have something listed as a reactant and as a product, it doesn't matter the order, they would cancel out. All I have to do is add my delta H values together then in order to get that delta H of reaction. So we have a delta H of reaction of negative 736.6 kilojoules. Okay, so here I need 4 aluminums. I have my 4 aluminums as a reactant. 3 MnO2s. My MnO2 is a product, so I first need to flip this reaction. And I'm going to change the sign of my delta H. But I also need 3 magnesium oxides, so that I'm going to multiply everything by 3, including my delta H value. So there's my second reactant. My first product is 2 aluminum oxides, which I have here, and 3 Mns, 3 manganese. So if you notice, I have 3 oxygens as a reactant, which will cancel 3 oxygens as a product. So when I add my reactions together, I should end up with my overall reaction. 4 aluminum, 3 manganese 4 oxide yields 2 aluminum oxide plus 3 manganese. The order doesn't matter as long as they're on the appropriate side of the arrow and there's the same amount. So now I'm just going to take my delta H values and add them together. And so my heat of reaction is negative 1789 kilojoules. One last example here. I need hydrogen peroxide as a reactant. Here I have it listed as a product. So the first thing I'm going to do is flip my reaction. And when I flip that reaction, my delta H value also flips. I need 2 hydrogen peroxides though, so I'm going to multiply everything by 2. So now I have my reactant. My first product is 2 waters, which is sitting right here, and I need 1 oxygen. I have oxygens in both of my reactions. This 1 oxygen as a reactant will cancel 1 as a product, leaving me that 1 oxygen I need as a product. I have 2 H2s as reactants and 2 H2s as products, so those would fully cancel, leaving me with 2 H2O2 going to 2 H2O and then 1 oxygen. So all I have to do is add my delta H values together. So really you're adding your reactions together to make sure that you've manipulated the steps correctly to get your overall reaction. So we have an answer of negative 196 kilojoules.